day 4 of Unit 4, Electron Configurations! I know you're excited for this. Today we're going to identify 4 quantum numbers. We're going to give them names and their symbols. We're going to be able to write those quantum numbers so we can describe an electron's position. Then we will be able to determine which electron is being identified by a set of quantum numbers. So, what is a quantum number? It describes the distribution of the electrons in atoms. Basically, it's a mailing address for electrons. We know the electrons are associated outside the nucleus in different energy levels, different sublevels, and they're somewhere there, right? Well, we can actually find them in their specific orbitals. And we do that by assigning them quantum numbers. So we assign them basically a mailing address. We can mail electrons. We know where they should be, or at least the area where they will be found. What are the 4 quantum numbers? The first one should be familiar. That's the principal quantum number. Its symbol is N, lowercase n. The second quantum number is the angular momentum quantum number. Its symbol is lowercase l. The third quantum number is the magnetic quantum number. Its symbol is m subscript l, also lowercase. The fourth quantum number is the electron spin quantum number. It is lowercase m subscript s. So let's tackle the first one, the principal quantum number. The principal quantum number cannot be 0. It can either be 1, 2, 3, 4, 5, etc. And as you know, they are the energy levels, which we've actually numbered on the side of your periodic table, and they represent each row. But it really is the energy level. It is described as the average distance of electrons to the nucleus. So what does that mean? That means it's the size of the atom and the electrons. The larger the value, the farther from the nucleus. That makes sense. You have to put in energy for an electron to get further away from the nucleus. Why? Because the nucleus is positive, as we already know, and the electrons are negative, as we already know, and we know positive and negative will attract each other. So we have to give energy for those electrons to get further and further away, which is why the energy levels increase as electrons get further away from the nucleus. The next quantum number is the angular momentum quantum number. That's the shape of the orbitals within the sublevels. So we have the principal quantum number, which is size, and now we have shape. So now we know the size, now we know the shape. So we are halfway there to finding where electrons will be found, their mailing address. So the angular momentum quantum number is shape. It depends on n, your principal quantum number. So it's 0 or n minus 1. So you can have 0 or you take your n and minus 1. So the first sublevel is S, and that is represented by L equals 0. Your next one would be the P sublevel, which is L equals 1. The next sublevel is D. L would be 2. The next sublevel is F. L would be 3. And then, of course, G. The L would be 4. And yes, it does exist. We haven't been everywhere in the universe. We don't know. It makes perfect sense that G exists. We are on 118 elements right now in the periodic table. When we get to 121, that's when we will use the G sublevel. So we're close. So it does exist. It's out there. For high school chemistry, we are only going to deal with S, P, D, and F. All right, let's do an example. So what is your L if you have N is 1, N is 2, N is 3? And what's N? N is the principal quantum number. So when N is 1, you'll take 1 minus 1, you get 0. So you have the S sublevel. When n is 2, you'll take 2 minus 1, gives you 1, and 0. So you'll have the s and p sublevels. Just like when you make your electron configuration, you have to include what you've already used, which in this case would be the s sublevel, and now the p sublevel. Let's keep going. Here's 3. You'll take 3 minus 1, which will leave you 2, 1, and 0, which corresponds with the s is 0, p is 1, and d is 2 sublevels. Okay, so we have the size, we have the shape. Now we need to know the orientation of the orbital in 3D space. And that is called the magnetic quantum number, and the symbol is m subscript L. Why is it called magnetic? Well, we noticed the orientation in space of these electrons in a magnetic field. So we decided to call it the magnetic quantum number. Little history, cool stuff. But let's move on. It is represented by the negative L, yes, L, the angular momentum quantum number, 0, and a positive quantum number, L. And what does that look like? Let's do an example. So, what's m of L, which is the magnetic quantum number? I want y'all to start thinking that when you see ml, you think of magnetic quantum number if the L is 1, L is 2, L is 3. So, when L is 1, we know that's 0. So m's of L is 0. Why is it 0? Well, because L of 1 gives you 0, and that means you have 1 orientation in 3D space. Let's look at another one. When L equals 1, you will have negative 1, 0, and positive 1. So you can have 3 orientations in space. And what does that orientation in space mean? I don't know if I talked on that. It is spinning around. Those sublevels are actually moving. They're not still. They're moving around the nucleus. They're moving around their allotted space, their sublevel, their energy level. So if L is 2, we'll have m's of L, negative 2, negative 1, 0, positive 1, positive 2. That's 5 orientations in space. And the last quantum number is the electron spin quantum number. And what does that mean? Literally, it says it for you. Electron spin. And we know that electrons spin in 2 different directions. We give them the value of plus 1/2 or minus 1/2. So those electrons are zipping around, going extremely fast in their allotted orbitals. And one electron is going one direction, let's call that clockwise, and another electron is going the opposite direction, let's call that counterclockwise. Electrons don't want to meet, they don't want to touch each other, so they spin opposite ways. Think of it like that. The plus 1/2 corresponds to the up spin of the electron. Like I said, let's call it clockwise. The negative 1/2 corresponds to the down spin of the electron, which is counterclockwise. So let's do some examples. List the values for n, for L and m's of L. N is the principal quantum number. L is the angular momentum quantum number. M's of L is the magnetic quantum number. For the 4D sublevel, well, what do I do? Well, we know that n is the principal quantum number, and this right here tells you which energy level it's in. So n would be 4. Now what about L? The shape of the sublevel. Well, it's given to us, D. And if you recall, D is 2. 0 would be S, 1 would be P, 2 would be D, 3 would be F. It's that simple. If you know the shape, which is designated as D in this case, of the sublevel, well, we know the L number is 2. So now we have 2 parts of the mailing address. Let's keep going. What's ML? ML would be, if you know your L, it would be that integer negative all the way to its positive. So it's -2, -1, 0, +1, +2. So we have the size, we have the shape, and we have the orientation in space of the orbital. Let's do another example. Write the 4 quantum numbers for each electron in a 2s orbital. Well, here we go again. What's the n? Well, it's given right there, Mr. Miller. It's that simple. N is 2. How about L? Do you remember what S is for L? It's 0. M's of L would therefore be 0 as well. And since we asked for 4 quantum numbers this time, we have to include the electron spin, which is ms. That would be +1/2 and -1/2. We know that there's 2 electrons in each orbital. So one has to be going up, upward arrow, spin up, and one has to be spinning down the opposite direction. If we're going to fill up that orbital, that is, because there could just be 1 electron in 1 orbital. But if we add another, they will spin opposite directions. So let's draw that out. We have a 2s, 1 electron spinning up, 1 electron spinning down. So let's talk about that electron spinning up. Its mailing address, or 4 quantum numbers, would be 2, principal quantum number, 0, the angular momentum quantum number, 0, which is the magnetic quantum number, and then a +1/2 spin for the electron spin quantum number. Well, we have another electron here. What would that be? It would be the exact same numbers, except the spin would be different. So it would be 2, 0, 0, -1/2. Let's do another one. What are the 4 quantum numbers for all electrons in the 3p orbital? How many electrons are in a p orbital? 6. So we have to have 6 different answers for this question. I've already given you all the information over here. I'll cover it real fast. 3 would be the principal quantum number. The angular momentum quantum number is 1 because p sublevel is 1. The magnetic quantum number would therefore be -1, 0, +1. And the electron spin quantum number would be +1/2 and -1/2. No surprise there, because we know there's 2 electrons in an orbital and one's spinning up, one's spinning down. So what would be the mailing address? Let's do 1. It would be 3 principal quantum number, 1 angular momentum quantum number. Let's just start on the negative side here, make it easy. -1 for the magnetic quantum number, and +1/2 for the spin. Well, we have a negative spin for that mailing address because there's 2 electrons in each orbital. So one's going up, one's going down. It'll be the same numbers, and then what changes is the spin, which is -1/2. Well, now we have a 0 here. That has to be included. So we have 3, 1, 0 +1/2. 3, 1, 0 -1/2. Well, guess what? We have a +1 that we have to include. So all the numbers are the same except for the +1 and the electron spin. So it's 3, 1, +1, electron spin going up. 3, 1, +1, -1/2, spin going down. Let's count. 1, 2, 3, 4, 5, and 6. I have 6 different quantum number mailing address for the 3p orbital because there's 6 electrons in a p orbital. All right. Go ahead and start worksheet 4.